Hi everyone. Yeah, thanks a lot for inviting me. Yeah, I'm very happy to be here. So my name is Ludovic Righetti. I'm a professor at New York University, and also since a month, I'm also affiliated with the ANITI, which is the Artificial Intelligence Institute in Toulouse. And yeah, so I'd like to present you some of my work. Yeah, so I'd like to show you a little bit of my work and mostly try to put it in the bigger framework of what's been happening to leg robots this past 10 years. So I typed my talk, is robotic locomotion a solved problem? And I'm asking this question because if you go in a robotics conference these days, this is what you will see. So you will see basically robots walking everywhere. And this is really new. So 5 years ago, you would never see robots walking everywhere in such a casually walking everywhere with like crowds around them and things like that. So one of the big questions is that what has happened, right? How did we get there? And the easy answer is say, well, we've made so much progress in science, right? This past few years that this is how we got there. And I was wondering if this is really the case, because if you look, right, leg robotics has a very long history. And in 1984, simpler humanoid robots were already able to walk. At Waseda University, they built a lot of humanoids, and they were already walking in 1984, right, which is 40 years ago. If you look a bit closer, the MIT Leg Lab had robots that were able to do crazy things, right? They were able to jump, to backflips, and these are all things that we see today in robots, and this is already 30 years ago. A bit closer, 20 years ago, if you look at Asimo, Asimo is the robot from Honda. It was able to run. It actually was the first robot that was able to run, first humanoid robot that was able to run. And if you compare that, for example, to the latest humanoid robot of Tesla, right, you could argue that Asimo is actually much more capable of movement, and it was 20 years ago. And if you look at the science of walking, right, most of the theory that we use today to get robots to walk already existed by 2006. So one of the questions I was wondering is why didn't we see tons of leg robots back then? Because everything was there. All the tools that we needed to some extent were already existed 20 years ago or before, right? And robots were already able to do very, very impressive things. So there's two things I'd like to try to explain you. One thing is that at the time, robots were able to do many impressive things, but are not able to adapt their behavior in real time. And I will explain what it means a bit later. And very few people actually had access to leg robots. So most of these robots, if you wanted one, you had to build your own, and it was really a small club, right? So to be part of the club, you had to be able to build your own leg robot. So very few people actually were able to do research in leg locomotion. So a long time ago, so let's say 20 years or more ago, this is how things would working to get the robots to walk. So what you would do is that you would compute offline. So before putting in on robot, all the movements that you wanted the robot to do, right? So you would compute what should be the motion of the leg, what should be the motion of the arms, and everything like that. So that's something that was done in advance. And once you had that, what you had a controller and some sort of stabilizer that was just trying to follow this plan. And then online, you were estimating the state of the robot, what was going on, and then you would just execute this plan. So the problem of that is that if something goes wrong and you need to adapt the motion of the robot, you cannot do that because you cannot stop, everything and then go back to your computer and recompute the thing. So that was one of the big problems, right? We were not able to do things online. And then one thing that happened is that we got access to very good optimization algorithms maybe 15 years ago. And we started to do what people call the optimization in the loop. So we started to optimize what I call with the quadratic programs, optimize what is the next thing that I should do given all the things that I would like to do now. So if I want to keep for example, the center of mass of the robot in a certain position, if I want to move my leg in a certain way, if I want to make sure that I create the right forces with the environment such that I don't slip or I don't fall, what should I do next? And only next. You only look at the next thing that you should send to, next thing you should ask your motors to do. And we were able to do that quite efficiently. I mean, when I say we is that as a community, right? And then we started to get robots able to balance really efficiently. So you can start to push robots around, and they were able to adapt their behavior such that it could balance when you start pushing them around. This is really nice. The problem is that and you could do that online, right? You could do that, so the robots will do that on the fly. This is really nice, but if you do that, well, you're not still able to step or make decisions on how to do something more complicated than just balance if you just look at the next thing you want to do. So then people started to optimize still offline a full trajectory. Say, how do I move the entire robot to achieve a complex task? And for example, we were able to do rather quickly. So in a few seconds, start to compute. If you want to go from A to B, this is what you need to do, right? You need to use your hands, you need to use your legs, and this is how you need to move your entire body to cross an obstacle. And then one of the big push that happened maybe over the 5-6 years is that suddenly we're able to do these things in real time. So basically, we were able to not only optimize full motions, but we start to optimize full motions in real time. And this is what you call model predictive control. And model predictive control is not a new idea, but it's been rather new that we can actually deploy that on complex robots in real time. And what does it actually mean? It means that at a given time, you measure the state of your system and you look at the environment. So for example, if your system is this dot x0, and they have an environment and you want to go from A to B, and then you optimize what should be the motion that you should have such that you can actually reach your goal while avoiding the obstacle, right? And then you get, so you plan in the future, right? You optimize for what will happen in the future. And then you start executing that on your robot. Obviously, a robot is not exactly what your model tells you or what your simulator tells you. So something, your actual execution is different. This is the black line I started to draw. And then you remeasure the state of the system, and then you see maybe the obstacles have moved or things have moved around. So what you do is that you re-optimize again. And then you get a new trajectory that tells you what is the new best thing you should do to achieve your goal, which is different from the previous one, right? And then you re-execute a little bit of that, and then you keep doing that forever. So what you do is basically you keep planning in the future what you should do. So the future can be more or less long. For working robots, typically you plan for the next 2 steps, what should be the behavior of the robot. And then you execute only a part of it, and then you remeasure and you re-optimize your thing. And in order to do that, you need to have very good optimizers that can do that in real time, right? So typically on a robot, you want to do that 100 times a second, or maybe 1,000 times a second if you can do that, right? To get really good performance. So, and once you can do that, you can start to do very dynamic things. So for example, on the left, this is an example we did in my lab. You can actually then start pushing a robot around. It's able to adapt its motion, its behavior. So it adapts where it puts its foot on the ground. It adapts when and where it puts its foot on the ground, so that it never falls. You can push it around, and it actually doesn't fall. So you can do very dynamic things. You can also ask a robot to do more complicated things. So for example, you ask it to reach. So here you're going to see Avadesh, the student, ask the robot to reach its hand. And then on the fly, the robot will figure out a way to do that without falling. So this is what you get, right? And this is done in real time without any pre-processing, right? Everything is done on the fly like this. To give you maybe something, maybe you know that you've seen, this is the exact technology that actually has been used by Boston Dynamics, right? They use this kind of idea of you optimize on the fly what you want to do, and this is how you get the robot to do a front flip like that. So this is a very powerful technology. So this is where we were at maybe, a few years ago. We were able to do these things online and do very complicated things. And then, so here what we optimize is the next trajectory. But then you always have to re-optimize each time something changes. So each time you measure a new state or the environment has changed, you have to recompute and re-optimize what you should do. So people say, okay, why don't we just optimize every possible configurations for every possible state I might be in, every possible obstacles I might see? Why don't I optimize that? So it's a much more complicated problem now, right? Because I have to optimize now a function a function that is going to map every possible state to an action, right? And this is what we call reinforcement learning. And this is really that really made a huge difference. But now the kind of irony is that we start to redo everything offline because it's way too expensive. So now we compute offline using a simulator. We simulate like millions of different ways of robots to do different behaviors for walking, for example. And then we encode into a neural network, which is our policy, the function that maps for every possible configuration of the environment and the state of the robot, what should the robot do, right? And you do that offline. So it can take a few hours, maybe a day, if you do very complicated things. And once you have that, then you have a policy that you can just query online, and it will actually perform a certain behavior, right? So there's no more deliberation online. Everything is done offline. But what is really nice when you do that is that you can suddenly fuse also in your policy all your sensory information. That's something we were not able to do before, is to fuse vision and all the sensors that you have inside your policy. So now your robot is able to react to visual changes of the environment, for example. And once you do that, so for example, on the left is our work done by my colleagues at the last NRS. And I think Philippe is one of the person who pushed that in Toulouse. To basically, you can learn very complicated behaviors, right? Now you can start to have a robot that can go upstairs, go down slopes, and it's completely, and you can compute a policy that can do all of these things on the fly, right? Which is really impressive. On the right side, it's a recent example of Unitree, which is a company we built this quadruped robot, where they're able also to do very dynamic things by training those using reinforcement learning to train these policies. More recently, I work with the colleagues at the last NRS, where we also included vision, start to have robots to do some sort of parkour, when robots are able to jump obstacles, decide, depending on the obstacles, if they need to go under or above, and this is all done automatically, right? So you can do very rich behaviors out of this technology. So I pitched, so we spent as a community, many years trying to do everything online and trying to recompute things online. And now we kind of took a step back and say, how about we brute force everything offline? And then we're going to have something we can use online where we don't have to optimize anything. The key thing that now people are working on is that we would like to do basically both, right? We would like to do everything offline using big data as much as we can to pre-compute everything that we can. And then online, we actually want to re-optimize a little bit such that we can adapt to anything we have not seen and ensure that we can get very safe behaviors, right? So this is kind of ongoing work we're doing in my lab. We also apply that to manipulation, right? So how do you actually do a bit of both? And by doing a bit of both, you can show that you can really improve a lot the behavior of robots. Here, there's an example where the robot needs to avoid an obstacle while reaching an object. And you can get very complicated behaviors that it's very hard to get if you use one or the other technique at once. Sorry, yeah, you can. The other thing is not to add more logical reasoning, right? You want robots to be able to have logical reasoning, understanding that if something happens, you need to logically change what you were doing and your steps such that you can actually achieve your task. And these are the next big things that people are working in leg locomotion and also in manipulation. But the one thing that we have not talked about at all is real learning, right? None of the things you're doing right now is really real learning because the robot is not actually doing something in the real world and adapting its behavior based on what it's learned from its own experiences, right? And that's really something that we don't know how to do in robotics yet. So I would say that's one of the big next thing that we need to look at if you really want to deploy robots in completely unknown environments, outside of the lab. So we can already do a lot of things, but we're still limited if we want to deploy everything in a complete environment. So the whole story I told you so far is to say that, well, basically we got better and better at optimizing things, right? You optimize the next step, we optimize the full trajectory, then we optimize entire functions for every possible solution. So the question is that was this just an algorithm problem, right? And here I would argue that actually the algorithm that maybe doesn't matter that much. What we got access over this past 20 years is great hardware. So we got better and better at getting access to hardware. We're not anymore a small club of people who have leg robots, but everybody can buy a robot that is really good for a very small price, or make their own robot very easily. Now we started to get a lot of software. So basically doing this optimization, doing this learning is very easy because we start to get very, very good software that we can use that is open source. We get very good simulators that you can parallelize that are open source. So a lot of things are like freely available or very low cost available to do research. So this, I think, actually really boosted the kind of research that we can do. So I would argue here is that the main thing, I think, why we see so many robots is because they've become accessible. And the technology, the optimizers, the learning environments, the simulators, they've been accessible to everyone. And because they've become accessible to everyone, the time from ideas to experiments has radically decreased. Now you can do what we would take a year or 2 years to do 10 years ago, we can do in a month now, because of all these things that exist. And it's actually much easier to actually do leg robotics. It's also much easier to get access to a leg robot. And here I would like to highlight an initiative that we started also with my colleagues at the LAS in Toulouse. It's the Open Dynamic Robot Initiative. You've seen a lot of these small robots that maybe you've never seen before. These are all robots that we have built, designed in our initiative, and that we have open source. So it means anyone can actually make them and copy them and use them in their own lab, which for us, it has really accelerated the research that we can do thanks to the availability of these robots. The last thing that I've not talked about at all is that now we have a lot of quadruped leg robots that move around. What are we going to do with those? There's lots of possible applications. And a lot of people are trying to get these robots to do applications. And here you might see things that you like, and you might see things that you don't like. And I guess the next big thing for us is to really think hard about what kind of robots we want and how do we want to use it, and what kind of robots we don't want, and how we should not use them. On that note, I'd like to thank my team, and thank you all for inviting me and for listening to my presentation. Thank you.